Good day, dear Tuti. In the first video, we sketched the graph of a circle with center at 3, 2 and a point on the circle at 1, 2. This allowed us to visualize the circle using GeoGebra. So we have a center of 3, 2 and we have a point on the circle 1, 2. And this is our circle. Did you notice a new component in the algebra pane? What did you observe? Yes, there is an equation representing the graph of the circle. Initially, this equation is given in its standard form. X minus h squared plus y minus k squared equals r squared. Substituting the center hk, which is 3, 2, and radius r equal to 2, so 2 squared is 4. So we now have x minus 3 squared plus y minus 2 squared equal to 4. GeoGebra also allows us to convert this standard form into the general form of the equation of the circle. To do this, please click on the circle component in GeoGebra, then go to Settings, and then Algebra. Then under the equation menu item here, select the general form. So this is the standard form, drop down menu, then click on the general form. The general form of a second degree equation is ax squared plus bxy plus cy squared plus dx plus ey plus f equal to 0, or ey is equal to f. However, since we are dealing with a circle, there is no xy term. See, there's no xy term here. So b is equal to 0. And the coefficients of x squared and y squared are equal. A is equal to c, and that is equal to 1 in this example. Hence, the general form of a circle is ax squared plus ay squared plus dx plus ey plus f equal to 0. In this video, you will learn how to determine the general form of the equation of a circle algebraically given the center and a point on the circle. Here's the example. Determine the general form of the equation of the circle whose center is 3, 2 and whose graph contains the point 1, 2. Step number 1. Start with the standard form of the equation of a circle. So we begin with the standard form of the circle's equation, which is x minus h squared plus y minus k squared is equal to r squared, where hk is the center of the circle, and then xy is any point on the circumference of the circle, and r is the radius of the circle, which can be calculated using the distance between the center and a point on the circle. Next, we substitute the known values for the center hk and the radius r, while keeping x and y as variables. Why? This allows us to generalize the equation and represent all points x, y lying on the circle. So again, this is the standard form of the equation of the circle. So here are our given. H is equal to 3, k is equal to 2, and r is equal to 2. Substituting into the standard form, so we now have x minus 3 squared plus y minus 2 squared is equal to 4. Here we retain x and y as variables because we're deriving the general equation that accounts for every possible point on the circle. Step number 3. Expand and simplify the standard form. Next, we expand the squared binomials into the standard form of the equation. Now, let's recall this special product. a minus b squared is equal to a squared negative 2ab positive b squared, or a squared minus 2ab plus b squared. Applying this to the terms in our equation, so our first squared binomial term is x minus 3 squared, where a is equal to x and b is equal to 3. So x minus 3 squared is equal to x squared minus 2 times x times 3, where a is equal to x and b is equal to 3, plus 3 squared, where b is equal to 3. Everything is equal to x squared negative 6x, because 2 times 3 is 6, plus 9, because 3 squared is 9. So again, x minus 3 squared is just equal to x squared negative 6x positive 9. Similarly, for the second squared binomial term, we have y minus 2 squared. Our a is equal to y and our b is equal to 2. So we have y squared minus 2 times y times 2, because a is equal to y and b is equal to 2, plus 2 squared is equal to y squared negative 4y, because 2 times 2 is 4. So the second term is negative 4y, then the last term is positive 4, because 2 squared is 4. So y minus 2 squared is just equal to y squared negative 4y positive 4. Next, we substitute the expanded expressions back into the standard form. So again, this is our standard form. This is our first squared binomial, and this is our second squared binomial. X minus 3 squared is just equal to x squared minus 6x plus 9, and y minus 2 squared is equal to y squared minus 4y plus 4 equals to 4. Next, we combine like terms. So we have x squared minus 6x plus y squared minus 4y plus 9 plus 4. So we combine like terms, the constant terms, equals 4. We copy x squared negative 6x plus y squared minus 4y, and then 9 plus 4 is 13. So we have positive 13 equals to 4. To rewrite the equation in general form, move all terms to one side by subtracting 4 from both sides. So again, all terms must be at the left side, and then we only have 0 at the right side. So again, subtracting 4 from both sides. So we subtract 4 here at the left, and so we subtract 4 here at the right. So 4 minus 4 is 0, and then copy all the terms here. So we have x squared negative 6x positive y squared negative 4y positive 13 minus 4. So again, all terms must be at the left side, and we only have 0 at the right side. And then we combine these two constant terms here. Right, so we combine these two constant terms here. So positive 13 minus 4 is 9. So copy the other terms. So we have x squared negative 6x positive y squared minus 4y. 13 minus 4 is positive 9, equal to 0. Finally, arrange the terms in standard polynomial order. So we have x squared positive y squared negative 6x negative 4y positive 9 equal to 0. Lastly, let us verify the result using GeoGebra. Examine the equation of the circle displayed in the algebra pane. So this one. Examine the equation of the circle displayed in the algebra pane. Compare it with the general form of the equation we derived manually. So we have x squared, we have positive y squared, we have negative 6x, negative 4y. And then we have positive 9 equal to 0 here, and in algebra we have equals negative 9. If GeoGebra displays a slightly different form, remember that this is the same equation, only written with the constant term transposed to the right side. So moving positive 9 to the right will give us this equation. Thus, these two equations here are algebraically equivalent. Conclusion: our manually derived equation is correct and matches the equation generated by GeoGebra. So thank you for watching, dear Tutie. Feel free to proceed to the next set of asynchronous tasks to continue your learning journey.